threshold. Okay, so it's a pleasure to welcome Professor Stefanie Jegelka from MIT, where she's been for a bit less than a year. And before that, she was at Berkeley in the AMP lab. And before that, she did a PhD in the Max Planck Institutes and ETH. And she's been doing some very interesting work recently on submodular functions and their applications in machine learning. So, thank you.
Thanks, Sujay. Well, thanks a lot for the invitation. It's great to be here. I spent 9 months at UT Austin once when I was an undergraduate student as an exchange student, so it's great to be back in Austin. I was happy to come back. So today I'll talk about submodular functions in machine learning, and my talk is structured very roughly into 2 parts. First, I'll give you a more general introduction about submodular functions in machine learning, sort of to get a bit more background, and then I'll show you sort of one specific example of how convexity and submodularity can play together in a very nice way. So let's start. So I'll talk about set functions. So for the rest of my talk, what will be important is that we'll have a ground set of items in all of those cases, and we'll be picking subsets of items, and then we'll have a function that scores these items. So this function is called a set function, and it could be, for example, the cost of buying these items together. It could be the utility of these items, the probability that these occur together, and so on and so forth. So we'll have this function, and we'll make the small assumption that this function evaluates to 0 at the empty set, and that we have some way of computing this function. Okay, just for complexity issues. So obviously this example is a bit constructed. So the question is, okay, is this actually something relevant? Does this actually occur in problems that we're interested in? So let me show you some more real-world examples of where subset selection problems and set functions occur. So the first one are discrete labeling problems. So say you have an image and you want to label the pixels with different categories of foreground and background. And essentially what you're doing is you're picking a set of pixels and saying these should take this label, and then you're picking another set and say these should take this label, and so on. So essentially you're just selecting sets of items or variables that should take a certain label. Similarly, we might be interested in, given a bunch of images, what's sort of the common thing in these images, what's the common object. So again, we're just sort of selecting a set of pixels that represents the common theme of all of those. Another class of examples is if we have large amounts of, say, videos, text, images, or something, we want to summarize them. So we want a very concise, small excerpt of the full thing that covers as much as possible of the content and is not redundant at the same way. And this is also relevant if you, for example, reply to search queries. Another example is if we want to do, for example, sensing or active learning. Essentially what we're looking for is a subset of variables or a subset of queries that we can pose that gives us as much information as possible about whatever we want to learn about. So all of these are essentially subset selection problems. In this case, my function has something like an information value of the query that I'm posing. And finally, another important sub-area is that of sparse estimation problems. So I have a noisy signal. I assume the signal is can be represented as a sparse combination of some basis vectors. So essentially I'm looking for the subset of basis vectors that represent this well. So essentially I'm looking for a vector that has lots of zeros, and I'm picking the set of entries that have non-zero values. So that again can be viewed as a subset selection problem. So in that case, if I have some more information, maybe I can also put a penalty function on what kinds of patterns of support this thing has. So all of these are very different problems. All of these can be uniformly phrased as some kind of subset selection problems with a different kind of scoring function, of course. And so we have some unified view of viewing them and writing them as optimizing some kind of scoring or penalty function. Now, like that, this is not a super useful view because I can write a lot of very hard problems in that framework. Just picking, optimizing some kind of set function or scoring function. So in general, this is not super helpful because it's very hard. On the other hand, many of these problems exhibit some additional properties that makes them much nicer. So for example, many of these problems have the property of submodularity, and we'll see that this property is extremely useful when you actually want to, for example, optimize these functions. There's also a different, additional work on how you can actually learn those functions. I don't have time to talk about that today. I'll mostly talk about optimization here. So submodularity is somehow nice. So why do we care about this? So let me just show you another quote from a paper from Lovaas in 1983, where he compared convex functions and submodular functions. He said, well, why are convex functions so important and so useful? And he said, essentially, because they occur in many models, and they are often essentially the only non-trivial property that can be stated to be common in all of these problems. The second thing is they are preserved under many operations and transformations. So if you prove something about a convex function, like a specific one, it often can be generalized to several other functions. And convexity still, while being so general, preserves enough structure to be mathematically beautiful and practically useful, give you practically useful theory. And moreover, that means you can efficiently minimize a convex function. And then he said, well, what about the discrete world? And he said that, so this is a quote from that paper, it is less apparent, but we claim and hope to prove to a certain extent that a similar role is played in discrete optimization by submodular set functions. They share the above 4 properties. So they are pretty general, and they can be efficiently minimized, and they have enough structure to have some interesting theory around them. So I'm trying to show you a little bit of that theory today. And of course, submodular functions, they don't only occur in machine learning. For example, they actually occur in a lot of different areas of applied mathematics. And it's sometimes nice to look at those and see, okay, these functions come up in these different areas. We can draw from these areas. So just sort of for the bigger picture, submodular functions actually are pretty general once you know about them. They occur in many different fields. Okay, so now let me tell you what is actually a submodular function. What is this very nice property that can help in many cases? So I'll just, for the roadmap today, I'll tell you a little bit more about the definition of submodular functions, show you some examples, and then we'll go into optimization. And the very big picture about optimization is essentially that if you want to maximize the function, you'll do some sort of greedy algorithm. If you want to minimize the function, you'll use the connections to convexity. Okay, so what is a submodular function? Let me just start out with an example. Let's start out with a problem of sensing. So we want to place sensors optimally. So now our ground set is the set of all locations where we could place sensors. And we want to essentially measure the temperature everywhere as well as possible to detect, for example, a fire outbreak as quickly as possible. And of course, we don't want to put too many sensors because it's expensive. So minimum number of sensors while maximum information is gained. So this information function that is out there, it has a useful property. And the property is characterized by what we call the marginal gain. So what's the marginal gain? It's simply the quantity by how much does my function value increase if I add another sensor to my set. So say I have these 2 sensors, the new sensor is coming in, how much does my function value increase by adding this new element? And now if my function is submodular, it exhibits what is called diminishing marginal gains. So what does this mean? Let's look at an example. So let's say we have 2 placements, A and B. In the first one, I have very few sensors. In the second one, I have already added more sensors to that. And now I look what happens to the marginal gains of a particular element. So here B is a superset of A. That's important. So the new sensor comes in, and on the left-hand side, I gain a lot from adding it because there's a lot of area that essentially I haven't covered yet. If I look on the right-hand side, the new sensor comes in, and actually I've pretty much covered everything. So I already know everything. The new one doesn't actually give me a lot of additional information. So formally what happens here is that I have a smaller subset of a bigger set B. If I add my element to the smaller set, I always gain more than if I add it to the bigger set. So I get these diminishing marginal gains. The more I know, the less I gain from an additional element. So that's a pretty intuitive notion. And here's the formal definition, that we have these subset and superset, and gain for the smaller set is always bigger. And this is pretty intuitive. It occurs in many different examples, as we'll see. But submodular functions, here it's a utility function. They can not only be utility functions, they can also be cost functions. So let's look at an example of cost functions. So let's say you're going to buy lunch today, and you add a drink to your lunch. So the increase in cost is probably the cost of that particular drink that you have. But it could be that you get lucky and the drink has a free refill. So every other drink that you want of that particular kind comes for free. So the marginal cost in this case of adding another drink is essentially zero. So for submodular cost functions, what we get is diminishing marginal costs. The more I buy, the less I essentially pay for every item on average. And this also models the economies of scale phenomenon in economics, for example. What we also see from this example is that the diminishing marginal gains is not necessarily uniform. That means if I now say would buy a cup of coffee in addition to that, I would probably not get the free refill bonus. So sort of similar elements together cost less. That's often what's the case. So here we would prefer to buy similar elements together. We prefer to get something that's somehow coherent or fits well together. Whereas in the sensor example, what we get is something like spread. Okay, so we get diminishing marginal costs. So again, the same definition. So now that we know what is a submodular function, let's look at some examples of where does submodularity actually occur. So the first example is a coverage example, and this is maybe the simplest way of modeling the sensor placement problem. Essentially, each of my sensor locations is a point, and around that point you have a disk that's sort of the area that's covered by that sensor, wherever you get information from that sensor. And now my scoring function is the area that's jointly covered by these disks. And obviously, if I have already covered a lot of space, so if I look at a larger set, the increase in coverage that I get, that's essentially the area, the green area that I get in addition, gets smaller and smaller and smaller because I've covered everything already. So proof by picture, this is a submodular function. For the sensor model, of course, this is a very crude approximation. Maybe there's a better way to write this. So here's another example how you could actually write the sensing model. So let's say we have hidden temperatures y everywhere, and these temperatures have spatial coherence, so hence this is a graphical model, and I have sort of the spatial coherence that two temperatures that are next to each other somehow correlate a lot, unless there's a wall in between maybe. But then what we can actually measure is not exactly the temperature at this location, but maybe the temperature plus some noise. So now what we are essentially picking is sort of x variables that we will observe, and the rest is unobserved. And we'll try to gain as much information about the unobserved variables. What would then in that case be a good utility function? So one possible utility function in this case is the following, that I look at essentially the mutual information between my unknown labels y and the variables x that I pick, which is the same as the decrease in uncertainty that I get after sensing. So if h of y is the entropy, the uncertainty about my unknown variables y, I subtract from it the uncertainty after sensing. And of course, that's sort of like the decrease in uncertainty that I get, and I want a maximal decrease in uncertainty. So this looks like a reasonable scoring function. And it turns out this function is a submodular function under a certain condition, and the condition is that the x variables are conditionally independent given the y. So in the model that I showed you on the previous slide, that is the case. And in this case, you can essentially show that this is a submodular function by showing that the entropy of discrete random variables is a submodular function. So if I pick a set of random variables and I look at their joint entropy, that's always going to be a submodular function. So we have another submodular function, actually two of them. Okay, here's another example. This is not sensing, but it's actually conceptually not too far away from the sensing and coverage. And this is influence maximization in social networks. So let's say you have a social network and you sort of seed information at particular nodes in that network. And then what happens is the information propagates through that network, so whomever you informed sort of informs their neighbors, and then they tell their friends and so on. So the information propagates through the network. And now what you want is you want to sort of optimally place a few points where you see the information so that it propagates as quickly as possible through the network. And your scoring function in this case would be sort of the expected number of nodes that it reaches after a certain amount of time. So this is a random process, hence you look at the expectation, and you sort of want to maximize that influence. And essentially this is a randomized coverage function. So sort of like, if you sort of condition on the randomness, it's just going to be a cover. And intuitively, it also looks like a sort of a coverage, like wherever it spreads, that's sort of where it's covered. So this, again, is a submodular function in the seed nodes that I'm picking. So this is now a function of the set of seed nodes that I'm picking. This is, again, a submodular function. So you can do sort of write the optimal influence maximization problem as a submodular optimization problem, maximizing this function. Maybe subject to the constraint that you don't want to see it more than k or something. Okay, so we've seen a few submodular functions now. We always showed, or sort of like, I gave you some intuition why this should be the case, that this particular inequality holds. So this is a diminishing marginal gains inequality, that this should hold in these different examples. There's another way of defining a submodular function which is equivalent to this inequality, and it's in fact slightly more general, and this is the union intersection inequality. So here I just take two arbitrary sets S and T, and I measure f of S and f of T, and this should always be larger or equal than f of the union plus f of the intersection. You can see that these are equivalent by doing a little bit of pattern matching. So if you make A union E S and B T, then you see that B union E is the union and f of A is the intersection. And with a little bit more reasoning, you see that these are actually equivalent. If one holds, then the other one holds as well. So that's another alternative definition. Let's go through one more example and use this particular definition to see that a function is submodular. So the function here is the graph cut function, so you've probably all seen this function. Here I'm picking a set of nodes. My ground set of items is the set of all nodes in a graph. I'm picking a set of nodes, and my cost function in this case is the set of edges that cross the boundary from picked to not picked nodes. So all the edges that I would have to cut out that set of nodes from my graph. And it's easier to look at this just in the smallest possible interesting graph. That's the graph with one edge. Let's look at this particular one for the moment, and let's look at what our inequality would mean. It would essentially mean picking the node U or picking the node V versus picking the union, and which is both of them, and the intersection is the empty set. And that's essentially the only interesting way this inequality here needs to be proved. So let's look at our graph cut function. So the graph cut function for two nodes is essentially 1, or the weight of that edge if I pick either one of the nodes. It's 0 if I pick both, or if I pick nothing. So if I pick one of them, the cost function will be the weight. If I pick the other one, the cost function will also be that weight, versus if I pick both of them, I'm not cutting any edge. If I pick none of them, I'm also not cutting any edge, so it's going to be 0. So overall, I see that if the edge weights are non-negative, this is going to be a submodular function, at least for that particular single edge. And now what is my big graph? My big graph is essentially a sum of these small edge functions. And now if a function is submodular, a sum of submodular functions is also submodular. And by that rule, you see essentially the inequality still goes through if you now sum up both sides. The big graph cut function is also a submodular function. So that's another prominent example of a submodular function by showing the other inequality. Okay, so we've seen a few examples. So let's now go on and let's look at how could we possibly solve optimization problems with these functions. So in most cases here, for example, we are looking at a min cut. Otherwise, you're looking at influence maximization or maximizing information or something like that. How would you optimize these functions? And if you think about the continuous world, what is very useful is like, for example, you want to solve a convex minimization problem, convexity is very useful. If you have a maximization problem, concavity is very useful. And somehow the Lovaas reference sort of pointed out that maybe submodular functions are somehow analogous to convex functions. But on the other hand, if you think about the diminishing returns really is a notion of discrete concavity. So the gain function is sort of like a discrete derivative, so my derivative shrinks, that's like having a concave function. So are submodular functions then really more like concave functions or more like convex functions? And essentially there are arguments for both ways. So you could either argue that actually submodularity is like a discrete notion of concavity, and there's some more properties related to concavity, for example, and when you construct a submodular, you can construct submodular functions from concave continuous functions. On the other hand, as we will see, submodular functions still have a lot to do with convex functions, and in fact, what they have to do with convex functions, as I'll show you, is sort of there's a convex extension, convex continuous extension of that function which is computable, and essentially there's a lot of duality theory that you can replicate for submodular functions that you have for convex functions. So in that case, sort of what some other researcher in this area wrote is sort of like, they look like concave functions, but somehow if you look at the duality inequalities, they always, for a concave function, occur on the wrong side. So somehow it's there, they behave more like a convex function. So essentially we have both, and we'll just exploit one way or the other. So if we talk about maximization, we'll exploit more of the concavity parts. If we talk about minimization, we'll exploit more of the convexity. Okay, so that said, let's talk about how would you actually optimize a submodular function, and we'll start with maximization. So where does submodular maximization come up? Essentially in all these problems like picking a set, summarization, inference maximization, maximizing information gain. We've also used it for object detection. Many other problems are submodular maximization problems. And just to show you a concrete example, a modeling example, that has been very popular is that of summarization or diversity maximization. So let's say you have a large set of collection of images or documents or something. You want a small synopsis that covers most of the content, but at the same time is not redundant. Same thing for search queries. You don't want to sort of like 10 times give the same result for the same query, like say for example Washington has many different meanings. You want to give, it's mostly like one for each meaning, maybe, or two. So how would you model this? And mostly the submodular functions that have been used there are sort of a combination of this relevance term and a diversity term. So relevance means that I'd like to cover my information as accurately as possible, so ideally I'd pick everything. And this is usually something like a coverage or something that's close to coverage essentially. And the other term, what it says is, well, I don't want redundancy. I don't want to bore the user with 10 times the same thing, like an epsilon difference. I want diversity in my replies. So how would I model diversity? So let me just show you two examples, two simple examples. The first one works if you know that your data set actually inherently has some kind of grouping or clustering structure, and this could be overlapping. So essentially you know that you have some kind of grouping structure in the cluster. And now intuitively so this could be, for example, different meanings of the word Washington or something like that. And now what you want is sort of, you don't want to pick too many times the same cluster. So what this function says is essentially for each, so now I'm picking the red points, and sort of for each new cluster that I'm hitting, I'm getting a score of 1, say. And if I pick another point from that cluster, I get less. Like for example, for the second point, I get only a score of 1/2, and for the third one, I get only a score of 1/3 or something like that. So I have sort of like only a concave, I have diminishing gains of picking stuff from the same cluster, versus if I pick stuff from different clusters, I get a new full score for every new cluster that I'm hitting. In the extreme case, you just count the number of clusters that you're hitting with your points. So obviously I'm trying to now spread across the different groups. So that's one simple example, and mostly you can then put sort of like any kind of concave, squashing, diminishing returns function on top of the number of points that you're picking from each cluster. here's another function that's slightly different that says that, well, I actually actively penalize if you pick similar points. So now I don't have any cluster structure, but for any points that I'm picking, I'm penalizing how similar they are to the other points that I'm picking. So here this S is a non-negative similarity score. The closer the points are, the more similar they are, the more penalty I get if I pick both of them at the same time. So that also forces me sort of to pick stuff that's spread out, that's not very similar to each other. Now these two functions, they have one crucial difference, and that is the following, that if I look at the left-hand side functions, the more points I'm picking, I'll still get an increase in score. It's going to level off. Maybe I'll not get any increase, but I'll never sort of get penalized for picking more and more points. So this function is always increasing, whereas this function on the right-hand side, the more I'm picking, sort of the more penalty I might be getting. So this function always decreases the more points I pick. This other one always increases the more points I pick. And in terms of optimization, that's a crucial difference. So what is going to be important if we do, yes?
So if you have a DS that's increasing,
yes,
RS is typically also increasing. Right?
Yes.
So you will just end up picking like very big subset.
Exactly. So yes, if you only have an increasing function and you don't put any constraints, the optimal solution is to pick everything. If you have a function that increases, maximize this function, yeah, sure, you'll pick the maximum possible thing. So if you have a function that increases, really what you'll want is something like a constraint. Don't pick more than k. Or don't pick more than like exceeding a certain budget if everything has a cost or something like that. So that's what you'll usually have. Otherwise the solution is trivial. I can solve it in constant time. Exactly. But maybe not very interestingly. So the other case where actually my function is decreasing again, that's like say finding a max cut in a graph. That function, I don't need any constraints. This may have an interesting solution by itself. Because if I pick too many, my gains will go down. Essentially, for example, if I combine this function with some kind of other relevance score, so I may get a function that sort of increases in the beginning, and as I pick more and more, sort of I don't get more relevance because I've covered everything, but I'll get this increased penalty for picking too many. So my function value sort of will go down again. And in that case, I don't necessarily need a constraint. I'll probably not pick everything. So that's the fundamental difference. And this is sort of, this difference is expressed by the notion of monotonicity. So if I find for a function that's monotone increasing, I'll always need constraints. So coverage, for example, is a function that's monotone increasing. Monotone increasing just means as my set grows, my function can never decrease. But then there are other functions, like for example a graph cut function. If I have a small set, I cut 3 edges. If I have a larger set, I cut more edges. And if my set gets really large, I cut very few edges, and you saw actually in the end it's a 0 again. So this function is not monotone, the left-hand side is monotone. So in terms of optimization, there's a crucial difference between those two, as I'll illustrate this to you. So let's for the moment assume our function has this monotonicity property, it's just increasing all the time. And in this case, even then, maximizing this function exactly is NP hard. I mean, with a constraint, let's say you have a cardinality constraint, you want to pick not more than k. So like max cover is one example of this. Max cover is an NP hard problem, so this is NP hard. However, the good news, and in fact the other one, like non-monotone, is also NP hard. If you think of max cut in a graph, that's also an NP hard problem. But the good news is that for these problems, still greedy, fairly simple to implement, greedy algorithms work very well in practice and in theory. So you get constant factor approximations. So here's one instance of this. So let's say we want to maximize our monotone function subject that we are picking not more than k items. The sort of theoretically optimal algorithm for solving this is a greedy algorithm. And it's like as simple as it gets. You pick the best element, and then you pick the element that gives you the best augmentation to your score. And then you pick the element that gives you the best augmentation to your score, and so on and so forth, until you have picked k, and that's it. So that's pretty easy, and all you ever have to do is sort of look at which element would give you the best increase, sort of the largest marginal gain of the remaining elements. So in illustration, let's say I want to sort of cover a few video segments. I have one item that covers a few of them, and then I pick sort of the guy that gives me the best increase. So this guy covers a lot what I've already covered, versus this guy covers a lot of new stuff, so I probably pick the blue one over the green one. and so on and so forth. So very simple algorithm, very easy to implement, and the question is, does it work? So I do this, obviously it's pretty simple, does it actually work? So here's an example for a sensing problem of comparing greedy with the optimal solution. And you see that actually greedy works surprisingly well. It's not always going to get you the optimal solution, it can't, but it always works very well. I mean, most of the time it works very well. I mean, so the question is, okay, this is empirically, can we say something in theory? So is there like any theory about this? And here's the theorem. So what this theorem says is that if I run my greedy algorithm and I pick like the set after k iterations at the set of size k, I'm not worse than a constant factor times the optimal value that I could reach. And this constant factor is about 63%. And I may be better, but in the worst case, I'm not going to be worse than 63%. And you see in the left-hand side picture, there's actually sometimes even better than that. And there's also like refined theory that explains when this actually works better than 63%. But this is the theory. So I get a constant factor approximation, yes?
So say I wanted a little more general approximation. So like S star also has k elements, right?
Yes.
But say I wanted to get the best score. Okay, so I want to pick, let's say, 2k elements.
Yeah.
But I want to compare how good I would be as compared to an optimal solution with k elements.
Yes.
So it's like
so you can
a little bit apples and oranges, but it's a different.
No, actually, it's a very good question. You can do this, and essentially, what's going to happen is, so you'll say this: you pick L elements here, and you have k here.
Yeah.
You'll get like a 1 minus 1 over e to the k over L, I believe. So it's going to be essentially approximating 1. So essentially this ratio of k versus L is going to come in the factor of the e, such that like the more elements you pick, the better this is going to become. So it's like, I just have to think that it's certainly like pick the ratio of k over L that makes this entire term larger as L grows, essentially, that way around. So you can actually, so you can take this into account to make this like better. So you can actually get better. And if you pick everything, of course, you're going to get 1.
Yeah.
Because that optimal solution will be somewhere among the elements that you've picked. There's also other variations of this that I didn't mention is, for example, if you find sort of only the approximately best element and not the next best augmentation, but sort of approximately next best augmentation, that sort of also will come into this factor here, but often you can still prove that it'll work fairly well. Okay. Yeah?
One more question. So in some other contexts, so a greedy just builds up a set and stops.
Yep.
Right, but then you could have like kind of a forward-backward thing where you say, okay, I've already built up this set. Now let me go back and see which is the most useless element given my current set. Remove it and add a. Yeah. Have people studied that kind of thing? So this thing is called a local search algorithm because at any like sort of you always see what you can increase and then you like decrease, but you always change your set from one step to the other by only one element. So in this particular case, it's known that in theory, sort of in the worst case, you cannot get better than 1 minus 1 over e. So in the very general case, this cannot get you better there. So in practice, it may still give you some mileage in some cases, but in this particular case, this is not going to get better. It's different if you talk about non-monotone maximization. So in that case, actually the local search, greedy will give you essentially no guarantees, local search will give you a guarantee. So in that case, actually it matters. Okay.
This is for maximizing submodular but non-monotone submodular?
This one is monotone. It's in the local search helps you if you have a non-monotone function. So you could do a local search in this case also, but sort of, and in practice it may actually help in some cases, but in theory there's like a lower bound that says you cannot do better than 1 minus 1 over e with a polynomial time.
Exponential time, no?
Yeah, so if you, you have.
No. Because you remember.
The question is whether it'll oscillate or not. But if it always strictly increases the value, it could still oscillate. You have to show that it doesn't. Yeah. So I don't actually know whether. So I don't know whether this would oscillate or not. I assume it probably wouldn't, but
no, even I haven't. If you increase the value, it could take exponential time, right?
Yes, true. Yeah. So I would still think that it wouldn't in this case because for a non-monotone function it doesn't. So probably it wouldn't. But you have to prove that that's true. That's another point.
Yeah.
So.
max cut with this?
Yeah, it could sort of like get smaller and
weighted max cut could take exponential.
If you do local search.
Yeah.
Yeah. Yes. Okay. Yes. So maybe you're right. Maybe in this case also it would. I just like I don't want to claim
PLS,
anything.
That's what they call PLS.
Yeah. Okay. So yeah, I don't know if this would. Maybe this would give you the optimal solution. You could possibly get it actually with that. Yeah. Okay. So. Another question is, so far I've talked about what if you want to maximize with a constraint that I'm not picking more than k. So what if I have some more complex constraints? For example, the following, that I have, again, the sensing problem, but now I'm picking not only which cameras I should activate, but also where they should point. So for each camera I have a range of different directions where they can point. So this camera has another one, and obviously I can pick point each camera only in one direction, so really I can pick only one direction per camera. So I have not only the constraint that I want to pick only k, I have the constraint that out of these k I can pick only one for each camera. So more semi-abstractly, what I have is that I have my ground set of elements, which is now all possible directions, and I can box them up, and essentially one box for each camera in this case, and I can pick only one from each box. So that's another constraint. It's called a partition matroid constraint, and this belongs to a larger family of constraints which are called matroid constraints. And for these you can still run greedy. Essentially what you do is you pick the next best element that won't violate your constraint, and then you stop when you have basically you cannot pick anything else. And in this case the greedy gives you something that's 1/2 times optimal. This is not the very best you can do in theory, but it's pretty reasonable. So the very best you can get in theory you would do by actually doing a continuous relaxation of the thing and a rounding procedure. That relaxation itself is very interesting because it's neither a convex nor a concave function that you're optimizing, but you're still sort of getting close enough. So you can handle many other types of constraints with greedy algorithms or friends of greedy algorithms, essentially slight variations thereof. The other question that I sort of alluded to is, what if my function is not monotone? In that case, I'll show you greedy is not always extremely useful. In that case, you can do other things. So first thing you can do is just pick a set at random, and it turns out it's not so bad actually. You get like a 1/4 approximation guarantee. If you pick, in expectation, if you pick a set of random. Of course, in practice, probably you want to do something smarter than that. So in practice, what you can do is either do a local search algorithm, so exactly what we talked about, which gives you a 1/3 approximation factor, and the optimal approximation factor you get by doing essentially a greedy algorithm in 2 directions, by taking 2 sets and growing one and shrinking the other, and in the end they'll meet, and that's going to be the solution. So this is called the double greedy algorithm. And that gives you the optimal possible approximation factor. In practice, local search and this thing work kind of similarly in many cases. Yes?
Are those guarantees for the constraint of picking no more than k, or is it for the main constraint as well?
Oh, so okay, so this is without constraints. Yeah, sorry, I should have said this. So this is without any constraints. You can do this with constraints, and in that case, essentially what you do is either a continuous relaxations or sort of a randomized greedy algorithm that mimics that thing in a discrete way. So what happens if I run greedy on a non-monotone function? So let's just look at a simple example, which is I have my coverage function, which is monotone increasing, and I subtract from it a cost function. And what this cost function does is it has like one cost per item, and I just subtract it from that, so non-negative costs. So here I want to cover that square, and I have 4 sensors, so that to keep it like tractable. Sensor 1 covers everything, but it's very expensive, and the other sensors together cover everything, and each of them is very cheap. And now what does the greedy algorithm do? So first of all, you can think about what would be the optimal solution for this problem. If you have to cover sort of as much as possible at as little cost as possible. So then what would the greedy algorithm do? So the greedy algorithm starts with the empty set, and it picks the guy that gives it the best mileage, like the best increase in gain. So that would be sensor 1. Sensor 1 gives you gain 40, versus all the others give you sort of single gain of something smaller than 40. So we'll pick sensor 1. And at that point it stops, because everything else you'd add to it doesn't get you any more coverage, because you cover everything and it only costs more. So all you'll have is sort of a decrease because you pay more and you don't get anything for it. So you'll stop. Versus the optimal solution would pick all the other ones and gets more than double the value actually. And you can tweak this example and make it sort of arbitrarily bad. And what this shows you is that in general, the greedy algorithm doesn't always work well for non-monotone functions. There are examples where it actually does, because the function sort of, at the range where you're operating, it sort of looks like a monotone function, but in general it does. So I wanted to mention one more thing about the greedy algorithms. Yes?
But in this case, you can make that as an abstract constraint and do something else. Right?
Yes, yes. So yes, you could solve that same problem with an abstract constraint. Yes, and yes, but then you sort of have to take into account the cost and coverage differently. And yes, that's true. So there is ways of solving this as a monotone maximization problem. So the other question that people have recently looked at is, okay, the greedy algorithm is all nice and good, but now if I have like a lot of elements, what do I have to do? I have to sort of like find the best ones. So I have to essentially do a search over all possible ones. Then I have to find the next best one. I have to again do a search over all possible augmentations and so on and so forth. And that's, if I have a lot of elements, even though it's simple, it's going to be expensive. So the question is, what can I do about that? And intuitively, let's say my choice, say, of the ith element very much depends on what I have chosen previously, because I'm looking for the best augmentation. And if I don't know what I've chosen previously, I might just choose the same thing that I have before. So sort of this like augmentation is not easy to assess. So the question is, what now can we run this, say, in a distributed fashion or parallel fashion or something like that? Pick these things in parallel. And the answer is it's tricky. In the worst case, it's tricky. On average, it's actually not so bad. So there's a few different ways you can address this. One is just to do like some stochastic or pick everything above a threshold. But if you really want to go distributed, in the worst case, it's hard. But there is algorithms, and essentially what they exploit is that the average case is not the worst case. So on average, not everything depends on everything else. And mostly the worst case is sort of a particular permutation, versus the average case permutation is much more friendly and has much more independence in there. So if you think about sensing, if I do something here and something here, that's relatively unrelated. It won't hurt me very much. And there's essentially two different approaches. One says that, well, I sort of preserve all the theoretical guarantees and I pick in parallel and I communicate when I have to, and essentially it'll always be preserving all the guarantees, but in the worst case it's going to become slow because I have to do a lot of communication. On the other hand, you can do something like a divide and conquer approach and say that, well, I'm always going to be fast, and in the worst case my solution is just not really going to be very good. So these are essentially two sort of ways of addressing that. On average, both of them work actually quite well. Okay, so we've talked about greedy algorithms, and all these greedy algorithms essentially exploit something like a concavity structure of your function. Now I want to talk a little bit about the connection between submodular functions and convex functions, and then I'll continue with that sort of with a more detailed example in the second part. So submodular minimization covers a sort of another set of problems where we are not looking to maximize spread or diversity, we're looking to sort of find coherent elements, such as clusters or small cuts in a graph, or sort of nice patterns that are somehow coherent, for example, and so on. So how do we do like submodular minimization? And here we'll use the relations to convexity, and what we'll work with is a relaxation. So what we'll need is we'll somehow need to go from the world of subsets and discrete vectors to continuous vectors. And the analogy is pretty easy. So if you have a set of elements, picking a subset, I could represent that subset equivalently by an indicator vector. And this indicator vector is now the binary vector. Now I have a vector. And all the vectors that I'll be talking about, they'll have as many dimension of that vector will be the same as number of elements in my ground set. So think about them as weights, element-wise weights, or indicator vectors, and so on. So that's going to be the representation. Now how do we go to a relaxation of my problem? So we sort of take our set problem, we place it in the world of vectors. So now what we have is a function that we can evaluate on binary vectors. These are our sets. But now we want something that we can evaluate everywhere. So we'll have to somehow maybe smartly interpolate this thing. And it turns out you can interpolate it in a way that gives you a convex function. So that's, and in fact we'll see you can actually compute that function. So you can do this in many cases, but we'll have to compute it. So this is actually computable. And this is sort of what it looks like, some piecewise linear convex function. Now we'll minimize this one. So what is this function? How could I get such a function? Let me give you an intuition. So let's say we have this binary vector function, and we get some kind of arbitrary vector, and now all we know is how to evaluate our function on binary vectors. So one idea would be, well, I take my vector and I convert it to something that looks like binary vectors. So I could write my vector as a combination of binary vectors. So I can do that. I can do this for every vector, and there's a unique way of doing this for every vector by essentially thresholding the vector at different values. So I get one set with 0.2 weight that is everything, and then the difference between the second smallest and the difference between the largest and the second smallest. So this gives me sort of a representation of my vector as a combination of binary vectors. And I can do this with any vector in a unique way. So you see, sort of all you need to do is sort your vector and look what's the difference between the largest and smallest, and so on and so forth. And then all I do is now have this representation. I evaluate my function at these binary vectors. So I do this. I know how to do this. This is easy to get. It's just a sorting. This thing also is easy to get. And that's it. So this is my extension. And this, in fact, I can do for any set function. So far, I've not used any kind of submodularity here. This is just an arbitrary definition. This definition can also be interpreted in another way. So we can think of our vector as sort of a bar plot. And now what I do is I randomly sample a threshold, and I pick all the elements that are above that threshold, that have entries above that threshold. Remember, every entry in that vector corresponds to an element in my ground set. So I pick that random threshold and pick everything above that. And you see that essentially I can only pick 3 different sets, and these are exactly the 3 different sets that I got on the previous slide. And now my extension is the expectation over f of f evaluated at the set at these random sets. Expectation over theta being uniform. And this representation can be written as an integral. So this Lovász extension that I just defined is equivalent to what's called the Choquet integral of that set function. So let me just show you, point out a few examples. I just want to go through these quickly. So here's one submodular function, which is 1 everywhere and 0 at the empty set. If you take the Lovász extension of that function, you'll get a function that always picks out the maximum element in your vector. Another prominent one that you may have seen is for a graph cut function. So I take again the cut function on my 2 elements. The Lovász extension of that cut function is the absolute difference between the entries of my vector. So we have only 2 entries, only 2 elements. So this is also called the total variation. That's the connection between total variation and graph cut. Okay, so why is this Lovász extension interesting? So far it's not clear that this is actually anything useful in terms of continuous optimization, the way it's written there. This is what's the gradient of this thing, and anything this is kind of very non-intuitive maybe for that matter. But this thing, it turns out, if the function is submodular, this has a different representation, and this representation is as a maximum of linear functions. And if you think about this thing, it's piecewise linear. A maximum of linear function is always piecewise linear. And in fact, this is a maximization problem over a very special polytope that I'll be defining. And the maximum of linear function is always a convex function. So this proves one direction, that if the function is submodular, then the Lovász extension is a convex function. So this equivalence only holds for a submodular function now, whereas the first one I can define for any set function. It's an if and only, so you can also show that if the Lovász extension is convex, the function must be a submodular function. Okay, so let's quickly look what is actually that particular polytope here that I haven't defined yet. And essentially all of submodular tractability of submodular minimization hinges upon the properties of that particular polytope and the convexity of the low-pass extension. So what is this thing? This thing relates very closely to what's called the submodular polyhedron. So that thing is just, it's a polyhedron which is defined by linear inequalities like every polyhedron, and these go with a submodular function. So what this means is that it's the set of all vectors. These vectors live in n, Rn, if I have n elements. These vectors have to be dominated by my submodular function. And I have one inequality for each subset of my ground set, so I have an exponential number of inequalities. So here's an example. So what this says is that I have two elements in this example, A and B. The first coordinate should be smaller than -1, so this gives me sort of a feasible set that's everything that's blue. The second coordinate should be smaller than 2, so that gives me something that's smaller than 2 in the YB coordinate. And what the third constraint says that the sum of the 2's, that's the set where I take both of them, has to be smaller or equal than 0. So that's my third constraint that should be satisfied. That is this other diagonal line here. So together, the points that satisfy all these three inequalities is the yellow region here. So this is the submodular polyhedron. It can be defined for every submodular functions. In 2D, it looks always something like that. Now the base polytope is a particular part of this thing. The base polytope is the one where the last inequality is satisfied with equality. So it's a particular phase of this thing, and these vectors all sum up to the same value. This is the base polytope. This is what it looks like in 3D, so usually it looks like in higher dimensions, something like that. So now my low-pass extension is defined via a linear optimization over this particular base polytope, yes?
So the low-pass extension can have extreme points that are not binary? Or it cannot?
The low-pass extension,
like this base polytope.
The base polytope can have extreme points that are, well, yes, so these corner points, yes, they are not binary necessarily. They are actually binary only in a particular case if we have what's called a matrix rank function, a submodular function, which has only increase of zeros and ones. Yes, so the corner points here are not necessarily integral. They are integral if your function has integral values, integer values.
Okay. But if your function has like rational values, you can make it integer.
Fraction.
Well, they will be, if your submodular function is fractional values, this thing will have fractional corner points.
I see. But we're going to minimize a convex function in the polytope anyway.
So the thing.
Minimize a linear.
So here's the thing. So this, I have my low-pass extension. The low-pass extension, well, where is it? Is defined via that polytope. But now I will be minimizing this function. So this function is just implicitly defined by this polytope. If you look at, later I'll show you a dual problem of that minimization problem. That's going to be an optimization problem over this polytope. But just sort of this thing is just a convex piecewise linear function, and what I'm arguing now that you can actually compute it. I showed you, but this is sort of the other direction. And what this actually is, and sort of the properties of that base polytope will be important sort of like for the dual problem. Yeah.
I think the point that we were trying to understand is if I will get a vertex, and the question is if the vertex will have integer or 0, 1 coordinates always, or it will have fractional coordinates.
Yeah, so I can actually, yes, and I can actually,
there will be fraction.
In fact, what the vertex looks like,
but it doesn't matter, they just look at the support of it, right? That's how
so
you get a set.
What the vertex actually looks like is like this. So these are the entries of the vertices of the polytope are differences in function values. So if your function has only integer values, this is going to be integer. If the function has non-integer values, this like real values, this is going to be a real value, most likely. Okay. So this is sort of where this comes from. But so yeah, so here's the story. Now we go back to our low-pass extension. Low-pass extension is a maximization over that polytope. That's just the definition. Now this thing has exponentially many constraints. So if I had just defined the low-pass extension like this, it would not be necessarily clear that I can actually compute it in polynomial time. And it turns out I can, and this is a very nice result by Jack Edmonds, that essentially linear optimization over this particular polytope is extremely nice. You can do it by essentially just sorting your vector x. This is almost an if and only if, so this type of matroid polytopes essentially correlates very much with a greedy algorithm giving you the optimal solution. So you can compute it, and essentially I'm gonna, in the interest of time, I'm gonna go a bit quickly here. So essentially what you do is you can sort your vector x, and now if you think about it, you want to maximize this dot product. So you want to be large wherever x is large. You want y to be large wherever x is large, and y can be small when x is small. So essentially you make y as large as possible where x is large, so for example in this coordinate. So you sort of go and satisfy the constraints coordinate by coordinate. So you go as far as possible in the most important coordinate, and then you go as large as possible, increase the second coordinate, and so on and so forth. So what this will correspond to is that you make a chain of sets, the first largest element and the first two large ones, and so on and so forth. This gives you a chain of sets, because x, again, is indexed by elements, so like ordering x gives you a permutation of the elements, and that's going to give you the entries in y. So from that also you know what the entries in these y's actually look like, and these are the corner points of the polytope. So now to complete the story, now we have a convex extension that we can actually compute. So we could minimize that convex extension. So we can also compute a subgradient of this thing essentially by the same way we do the greedy algorithm. The subgradient of a max of linear functions is the argmax function. So you can compute it. So you can use a convex optimization algorithm on it. It's a non-smooth problem, so it's not necessarily going to be very fast, but you can do it. The other question is, now I minimize this, does it necessarily give me an optimal solution to this one? So I have this relaxation, but relaxation is not always exact. So it turns out, in this particular case, this is actually exact. So this is the second amazing thing. This is actually exact, and the rounding is super easy. So you solve this problem, and then you pick all the elements that have entries larger than 0. And that's going to be the optimal solution. And that also was essentially the proof that, well, together with the ellipsoid algorithm, that submodular problems can be minimization can be done in polynomial time. So this was a sort of answered an open question in the 80s using the ellipsoid method. And essentially, well, pretty much all the submodular minimization algorithms rely on the fact that you can compute the Lovász extension. The Lovász extension gives you the exact minimization, and you can compute subgradients of the Lovász extension. And these methods, essentially, you could use the ellipsoid method. It's not ultra fast, it's doable. You can use a subgradient method also. And now, after that, there was the question, well, what about combinatorial methods for solving this problem? Like, there's special cases of submodular minimizations, like minimum cut, that have nice combinatorial algorithms. So what about that? And so people worked hard on getting like a polynomial time combinatorial algorithms, and in fact, like about 20 years later, it was there. And what these combinatorial algorithms rely on is essentially they don't minimize the Lovász extension, but they look at the dual problem of this thing, and the dual problem is going to be an optimization problem over the base polytope, and they solve that with combinatorial methods, network flow type methods. Because essentially the problem is that you have to stay in the polytope, so that's the challenge. So these are polynomial time combinatorial methods. Their running times are about n to the 5, n to the 6 in the worst case. There has been recent progress on this. So this is a paper from Fox 2015, where actually they could improve on these running times. And this method is a combination of a new ellipsoid, like cutting plane method, and combinatorial methods.
What is T?
T is the time to evaluate one submodular function. So you put it in sort of as an oracle time, which also, depending on the function, this could be cheaper or less cheap. So then there's another class of algorithm that uses a slightly different relaxation, and I'll tell you about this in the next part, which is the minimum norm point algorithm, which solves a slightly different problem from just minimizing the low-pass extension. So I wanted to tell you a little bit about constraints. I'm going to skip that part to finish in time. So you can also solve constraint problems. You cannot solve them with convex optimization anymore. They're in general hard, but it turns out in practice there's like most of them are actually not as hard as it turns out. So let me just summarize this first introduction. So I showed you about like submodular functions, and I showed you submodular maximization can often be solved via greedy algorithms. Submodular minimization mostly relies on analogies and close connections to convex optimization. And essentially it relies on the fact that you have the low-pass extension. So I'll take a quick break now, and then in the second part I'll show you actually a different relaxation for solving the submodular minimization problem that also uses the low-pass extension, but a more smooth version of it. So you can now take a little breath, and then we'll continue with more with convexity and submodularity.
How long did we go?